Hi, I'm Mark Weitzman, and welcome back to my series of videos on symmetry and group theory in physics. Today we're going to start with discussing symmetry transformations. Sometimes this can be confusing when you're trying to distinguish between reflections and rotations and what moves the coordinates of the particles. Are we just interchanging particles or are we just interchanging coordinates? So today I want to go through in a very elementary and systematic way one approach. So let's start with a simple system. We have a system with a mass m connected by a spring to another system with a mass m. And we're going to take our x-axis like this, and our origin, let's say this is the equilibrium position of the spring. This is the equilibrium position of the spring, equal masses. We're going to assume that this is a one-dimensional problem, that we can only have motion this way. This is our origin of our coordinate system, which is like right in the middle of the spring when it's in equilibrium. So the first question to ask is, what are the symmetries of this system? And even before I ask that, how do we describe the coordinates in the system? Well, first thing is I'm going to call this mass 1, and I'm going to call this mass 2. And we're not worried about the equilibrium coordinates, but what we're interested in is if this mass moves, let's say, this way a little bit, we're going to call this x1. That's how much it's moved from its equilibrium position. And if this one moves like x2, that's how much it moves from its equilibrium position. So that's our coordinates that we're going to describe the system. And so my first question is, and this came up in vibration and waves course, what is the symmetry of this system? Well, it's fairly obvious that the main symmetry is a reflection symmetry. And so first we have a reflection symmetry. And when I say reflection symmetry, I'm referring to the equilibrium position of the spring. So I'm talking about like this mass over here would become this mass, and this mass would become this mass, and you can't distinguish it. So what happens is we basically say that before the symmetry, we describe the system by a vector. Let's call it x1, comma x2. x1 is, as I noted, the amount that the mass 1 is away from this equilibrium position. And mass 1 always refers to this side. Even if we reflect, this is still mass 1, and this is mass 2 away from that. So we'll call this a displacement vector chi, whatever. I'm not very good at writing Greek letters, as you can see. And under the reflection R, about this axis, even though it's a 1D problem, we're reflecting about this axis. This is going to go to minus x2, comma, minus x1. Sorry. So why is that? Well, if this is displaced a small amount here to here, when we reflect, it's going to displace the small amount to the left. And so our new coordinate for the particle that's on the left side is going to be over here, which is minus x2. Remember, x points in that direction. So the coordinate of particle 1 is now going to be minus x2. Likewise, this went to this side, and this is going to be minus x1. And you can see the same way if we had described a different situation. Let's say it was over here, x1, and it was over here, x2. It would be the same thing. When we reflect, it goes like that, and it's going to be over here, and x2 is going to be equal to minus x1 and minus x2. So that is the effect of our symmetry transformation. That's really the only transformation. I know some people think about rotating and this and that, but really it's a 1D problem, and all we can do is just reflect. And this reflection will keep the Hamiltonian, the potential energy, and everything about the system the same. So it preserves, or mathematically we would say it commutes with the Hamiltonian. And that's just the kinetic energy plus the potential energy. And here we have the potential energy system. It's a spring. It's just 1/2 kx squared, you know, the extra displacement squared. We're not going to do the dynamics of this. Now, so this is what we call the easiest group in the world. It's called a 2-element group. I know I haven't defined a group, but we'll do that next lecture. 2-element group. And the 2 elements of the groups are, I'll call E and R. E in group theory will usually stand for the identity element. That comes from German. And R is the only other element of the group, is the reflection. And this thing, the group element, has the property E does nothing, and R squared, when we reflect twice, is equal to E. That tells us everything we need to know about the group. You can also think of R as a parity operator. So one of the things, just to give you a preview of what we're going to do, is one of the things here in this very simple system is we want to represent this transformation by matrices. By the way, this was under R. Under E, obviously, x1, x2 goes to x1, x2. Nothing changes. I won't always specify what the transformation does under E. So the matrix representation is, and I'll call this D, and I'll call this, let me see what notation I used. Let's just call this D2E. D is what we usually use as the symbol for the representation matrices or group elements. I'll discuss this more thoroughly in a while, but basically for each element of the group, we're going to map to a matrix which is going to represent that element on the vector space of the group. In this case, the vector space are just these two this displacement vector, x1 and x2. Once we know x1 and x2, we know everything about the system. So representation of the identity element is just the identity matrix. And the 2 here stands for 2 dimensions, because we have 2 coordinates, so we're going to represent our thing by 2 dimensions. And then the matrix that we're going to represent R is given by 0, -1, -1, 0. Now you can easily see this if you take D2R, apply it to our vector x1, x2, you're going to get -x2 -x1. So that's exactly what this means. Sometimes we write them as row vectors, sometimes we write them as column vectors. But when we use matrices, we'll usually use column vectors, but that's all the type of nonsense we don't have to worry about. So this is a representation of this two-element group. Now, the interesting thing is that this representation is too complicated, because really we'll find out that for groups that are this small, what we call abelian groups, groups where all the elements commute, there's only two elements here, but ER is R and RE is R, and that's it. So this is what we call a commutative group. All the irreducible representations are one-dimensional, and I'll even write them out right now on what the irreducible representations are. So let's call this E, let's call this R, let's call this D1 and D1 prime. There's only two ways to represent this group. One is everything is represented by 1, just a number. That doesn't really do much, but that's basically the identity. And the other is where we represent the identity by 1, which we always do, but we represent the reflection by -1. Now, all of this may seem like excessively pedantic and unnecessary, but when we get to more complicated groups, these ideas will generalize and be important. Right now, what we're saying is basically there are two types of symmetry functions that can represent this group. In one, the function is completely symmetric, and in the other, the function is anti-symmetric. Now, we already know, I mean, we don't need group theory for this, but we already know that every function of a variable x, we can write it as 1/2 f of x plus f of minus x plus 1/2 f of x minus f of minus x. And we know that this function is symmetric. And this function is anti-symmetric. So this goes back to the simple idea in quantum mechanics or in any area of physics that if we have a one-dimensional function, we can represent it as a sum of a symmetric function and the sum of an anti-symmetric function. There's only two symmetries possible for a two-element group, for something that's just parity and do nothing. So that covers this situation here. Basically, the motion of the spring, you can either have sort of like, they'll both be like this, which is end up not vibrating at all. This is what's called a translation symmetry. Or the other alternative is they're both opposite to each other. And this is the vibrational mode. And of course, on the other side of it, it goes like this. So this is sort of the idea of what the symmetries are, is what we want to do is one, at least for small oscillation problems, we want to get rid of the translational and rotational symmetries because we know that that's not important to us in terms of oscillations. And then we want to find out what kind of oscillations the system allows. In this particular case, it's such a simple system, there's only one mode allowed. But when we get bigger matrices, we'll find that they're reducible into different symmetries. Each symmetry, each irreducible symmetry will represent an eigenfunction, and it will be different than some of the other eigenfunctions. So that's sort of where we're headed. And right now, I want to go from this simple one-dimensional example to a two-dimensional example. So let's say we have the same thing again. We have a mass M on a spring, and this is the equilibrium position. But now we're going to allow our x coordinates are like this and our y coordinates are like this. We're going to allow small oscillations where this mass can go like this, and maybe this mass can go like that. This is supposed to be small relative to the spring size, but I'm just drawing it larger. So they can go in both the x and y directions. So now our displacement vector, should have put a vector on it before, we're going to write it as x1, y1, x2, y2. And again, this is particle 1, and this is particle 2. So the symmetries this time will be a little bit more complicated. So let's try and figure out what are the symmetries of this particular thing in 2 dimensions. Once again, when we think of symmetries, always go back to the equilibrium position. We'll worry about the action on the coordinates later, but this is the equilibrium position. Let's say this is the origin of our system. So, again, x, y. So there are 3 obvious symmetries, well, 4 obvious symmetries. The first one we'll say is E. We do nothing, leave it alone. The second one we'll call Rx. This is just a reflection about the x-axis, and you can see that it sort of does nothing on this thing, because when we reflect, nothing happens to these 2 masses. They don't even change positions, but about the x-axis. But we'll find that the coordinates actually do change. The y-coordinates change, the x-coordinates don't. The third symmetry that we can have, we'll call it Ry, is a reflection about this axis. Same one we had earlier. So that's the reflection symmetry. And finally, there's another symmetry which I'll call R pi, which is a rotation. I can literally rotate this to here, and I can rotate this to there. And the rotation symmetry, it turns out, is in 2 dimensions. It's the same thing as the product of Rx, Ry. But what we have is a 4-element group. It's a little bit more complicated than our 2-element group, but it's still what we call, we have a 4-element group of symmetries. That's what we call abelian. This is named after Abel, who was a mathematician in the early 18th century, who with Galois is sort of responsible for founding group theory. And an abelian group simply means it's commutative. You know, AB equals BA. Non-abelian means there exists an A comma B in the group that AB is unequal to BA. Okay. We'll find out as we go along that these are the more interesting groups. But the small groups, it turns out groups of elements, number of elements is 1, 2, 3, 4, 5 are all abelian. It takes 6 elements before we get our first non-abelian group, and we'll talk about that soon. Now, what I want to do is, I just want to talk about how we represent this group with matrices. So, I don't think I need this anymore. So we have a 4-component displacement vector, x1, y1 for particle 1, which is always on the left, x2, y2 are the coordinates for the particle that's on the right. You might say, how do we know if something's on the left or on the right? Well, these are small oscillations. So this should be close to this equilibrium position, and this should be close to this equilibrium position. Now I want to, just looking at this diagram, let's say I apply Rx to that diagram. It just makes, okay. So if I apply the identity element, I just get back the same diagram. So x1, sorry, x1, y1, x2, y2 goes to, nothing changes, x1, y1, x2, y2. And the matrix that's going to represent that is just going to be a 4x4 identity matrix, 1, 1, 1, 1. Now let's do Rx. If we flip about this axis, the particles still remain on the same side, but the 2 vector, it goes like this. Now it was pointing up, so it's now going to be pointing down. This is the origin again. This was pointing that way, so it's going to be pointing that way. Okay, so M1, M2. So with that, we have x1, y1, x2, y2 goes to, and so the particles stay on the same side they were on, and the x coordinates don't change, but the y is reverse. So we get x1 minus y1, x2 minus y2. I'm doing this painfully slowly, and I hope doesn't bother people, but I found that sometimes students get confused with these very, very simple things. So I just want to do it real slowly. So the matrix that represents this is 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. And you do your standard linear algebra thing. If you want to know what the first column is of the matrix that represents this transformation, take the first basis vector, which is just x1 is 1 and all these others are 0. Where does that go? That goes to 1 and all the others are 0, so we get that. Where does the basis element, which is y1, go to? If this is 1 and all the others are 0, it goes to minus 1, and all the others are 0, so we have minus 1. x2 again, 1, and y2 minus 1. So this is equal to d4, it's a 4-dimensional representation of E. This is equal to d4 of Rx. Let's do Ry. On the Ry, now we're flipping about this axis, and basically what was here is now going to become like that. So we're going to get this, and what was here is now going to be like that. So under this transformation, x1, y1, x2, y2 goes to minus x2, y2, minus x1, y1. And again, what happens here are two things. One, the particles interchange motion. So this is x1. How do we get this? We take what was here, the x value of this, and now it gets reversed, so it becomes minus x2. y1, on the other hand, doesn't get reversed, but it does become part of y2. And same thing for x2 and y2. So we get the matrix which represents this. And again, if you multiplied this by a vector x1, y1, x2, y2, you'll end up getting that. And you can see, for instance, if you want to know what the second vector is, act on the second basis element. So if we just have y1 as 1 and all the other ones are 0, we're going to end up with y1 in the fourth position. We're going to end up with 0, 0, 0, 1. That's the second column. Okay, and then our final one is rotation. I'll try and in these videos use small r for reflections and large r's for rotations, and I'll usually attach the angle to the rotations. So what happens here, it's not too hard to see. Let me draw it here. Under a rotation, this goes like that. So it becomes like this. And what was here goes to here. So basically it's just, as I said, r pi is rx and ry. And if you work it out, this one, I wonder if I wrote that one down right. Minus x2, y2, minus x1, y1. This one's just going to have minus x2, minus y2, minus x1, minus y1. This is going to be a four-dimensional representation of r pi. Now I know we haven't even talked about representation of group elements, but I just want to do sort of an example of how coordinates get transformed.